In this discussion video, we will talk about testing for continuity. So a key fact is that the following types of functions are continuous everywhere in their domain. So polynomials, rational functions, which are polynomials divided by polynomials, root functions, things like square roots, cube roots, trig functions, inverse trig functions, exponential functions, and logarithmic functions. All right, so we will want to keep that fact in mind as we look at worksheet 4, problem number 1b, which asks us to express in interval notation the values for which each function is continuous. So part B has this function, x to the 4 minus 16 over x squared minus 4. So I want to begin by giving you a minute to try this. 4, 3, 2, 1. Pause the video for a minute to try this question on your own first. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for a minute. So the key thing here is this is just a polynomial over a polynomial, meaning this is a rational function. It is a rational function, which means it should be continuous everywhere that's in its domain. So let's find the domain. Let's find the domain of that function f. So we are working with b here. So the only thing that I have to worry about is the denominator, x squared minus 4, should not be equal to 0. And that means x cannot be equal to positive or negative 2. Okay, so those are the only values that are not in the domain of f. Those are going to be the only places our function is not continuous. So f is continuous. I could probably even do this without a number line on, let's see, negative infinity up to negative 2, not including negative 2, union, and then negative 2 up to 2, union 2 up to infinity. All right, and that is all the places, all the numbers where our function is continuous. All of these places are in the domain of this function. All right, let's look at problem number 3b from that same worksheet, worksheet 4. This question asks us to choose values of a and b such that the function is continuous. And f of x here is a piecewise function. So each of these parts of the piecewise function is one of these functions that we said are continuous everywhere in their domain. The first two pieces are just polynomials. Keep in mind the b and the a are just some numbers, like it might be x squared minus 3 and 2x plus 7. They're just some numbers. And then I have a root function after that. So those pieces individually should be continuous. But so the only issue is that when I jump or transition from one piece to another piece, this is the key fact, piecewise functions can also be discontinuous at those transition points where you shift from one piece to another piece. So I'll get us started with an idea for b, and then I'll give you a chance to try it. So our function f is going to be continuous everywhere, because each of the pieces is continuous everywhere on their domain, everywhere, except maybe if there's anything not in the domain of those functions. And with the first two polynomials, well, polynomials have a domain of everything. And with the root function, I would only have to worry about the inside of the root being negative. But because x is greater than or equal to 6 on this part of it, that's not going to happen with the root. So the only things I have to worry about is maybe those transition points at 4 and 6, where I switch from one piece to another piece. All right, and that is what I want you to test for. Is it going to be continuous at those places? Okay, so pause the video for 4 minutes. 4, 3, 2, 1. Pause it and try this one for 4 minutes. Alrighty, so hopefully you did that. Hopefully you paused it and tried this for about 4 minutes. So let's talk about x equals 4 first, and we'll make sure it's continuous there, and then we'll do the same thing for 6. So at x equals 4, let's take the limit as x approaches 4 from the right of our function. We will also take the limit as x approaches 4 from the left of our function, and we also need to plug in 4 into our function. And we need all three of these things to be the same for our function to be continuous. at x equals 4. Okay, so first let's do the limit as we approach 4 from the right. As you approach 4 from the right, let's actually draw a number line to help us visualize this. So I'll draw a number line, and let's put the transition points on it, 4 and 6. To the left of 4, we have the piece x squared minus b. In between 4 and 6, it's 2x plus a, and then after that, it's that root function, a times root x plus 10, and then plus b. Okay, so if we're approaching 4 from the right, we're getting super, super close to 4, but we're on the right side of 4. That is over here. We are in this middle piece, 2x plus a. And now let's plug the 4 in to get 2 times 4 plus a, which is 8 plus a. Nice. Let's do the limit as you approach 4 from the left. The limit as x approaches 4 from the left. On the left-hand side of 4, we're getting really, really close to 4, but on the left of 4, that is over here. We're going to use the piece x squared minus b. And plugging in 4, we'll get 4 squared minus b, which is 16 minus b. Finally, I plug 4 into my function straight up, and that's going to be the middle piece, because the middle piece is the part where it says x is equal to 4. So I would plug 4 into that, get 2 times 4 plus a, which we've already done. That was 8 plus a. So because of this, we need all three of these to be the same. We will set 8 plus a equals 16 minus b. That will ensure that our function is continuous at x equals 4. All right, now let's do it for x equals 6. In fact, let's zoom it out a little bit so I can still see it. So for x equals 6, we will do the limit as x approaches 6 from the right. We will do the limit as x approaches 6 from the left. And we will also plug 6 into our function. So let's do the limit as x approaches 6 from the right. X approaches 6 from the right. On the right-hand side of 6, if I get really, really close to 6, that is this part of the number line. So we're going to use the root function, a times root x plus 10, plus 10, and then plus b. All right, plus b. And if I plug 6 into this now, we get a times root 16 plus b, which is 4a plus b. Now let's do the limit as we approach 6 from the left. The limit as x approaches 6 from the left. On the left side of 6, if I get really, really close to 6, but on the left, that's going to be the piece 2x plus a. And if I plug 6 into that, we get 2 times 6 plus a, which is 12 plus a. And then finally, plugging 6 into my function, we would plug in the bottom piece, because that's where x is equal to 6. But that would give us the same square root expression. It would give us a times root 16 plus b, which is 4a plus b. So we need to set these three things equal as well. So let's set the 4a plus b equal to the 12 plus a. And what this gives us now is two equations. So we have a system of equations. Okay, if I work with this equation first, 4a plus b equals 12 plus a, if I rearrange it and move the a to the left, we get 3a plus b equals 12. In fact, let me put that in a different color. All right, so 3a plus b equals 12. If I do the same thing with this other equation, let's move the a and the b to the left-hand side. So we'll get a plus b. And then let's move 8 to the right-hand side. That'll give us 8 on the right. All right, so I have the system of equations. There's a few ways I can solve it, but one is I could subtract these two equations, and that'll cancel the b's, and it'll leave me with 2a on the left, because 3a minus a is 2a, and then 12 minus 8 is 4. If I divide by 2, we get a equals 2, and we could plug this into either equation to get b. So if I plug it into the second equation, we get 2 plus b equals 8. That means b equals 6. So a equals 2 and b equals 6. Those are the values that will guarantee that our function f is continuous. So one last comment that I want to make is, when a problem says a function is just straight up continuous, it doesn't specify where, it's talking about continuous everywhere. And we found the values of a and b that guarantee that.